Okay, so welcome to everyone. My name is Xavier Rivas, and I'm here with my colleague Francesca Estragues, and we are both applications engineers in MPS Barcelona. And we are going to explain how MPS solutions can help you to meet code rank requirements in ADAS designs. Today's webinar is handled by Francesca Estragues and Xavier Rivas, that are two applications engineers that are working for the automotive product line in MPS Barcelona. And online there is Jens Hedrick and Christian Cook, that are two field applications engineers of Central Europe. Here in this slide, you can find their contacts, and if you have some remaining doubt or you need any kind of support, do not hesitate to contact them. Now, once these presentations are done, let's start with this webinar. As it has been said, the goal of this webinar is to present an MPS solution to solve the code rank requirements in ADAS designs. In order to clearly achieve this goal, firstly, we are going to review the main requirements of ADAS designs and the meaning of code rank. Then, as a kind of state of the art, we will present the previous solution that was released by MPS, that is what's known as a pre-bus reference design. However, as it will be seen later, this previous solution presents some limitations that are going to be solved by the solution that we'll present at the last sections, that is the MPQ8875 back-bus converter. So now let's start with introduction. As it's known, the ADAS driver assistance systems, also known as ADAS, are of highly interest in today's automotive market. Nowadays, the number of sensors and cameras that are placed into this kind of designs is increasing a lot in order to monitor every single part of the car. As a consequence, there is also an increase on the power demand of ADAS. On the other hand, each sensor inside these systems have their own specific input voltage requirement that can be around 10 volts for some cameras, for example. This is the battery voltage must be down converted to different voltage levels to supply the required power to all the systems. Due to that, the ADAS designs must ensure the following aspects. First, the design must be efficient in order to reduce the power loss. Second, the design must occupy the minimum amount of area. And thirdly, it must ensure the functionalities during all the time that the car is in use. In other words, during start-stop event, there are some functionalities that must be able to operate. This last requirement brings us to the problem that we'll try to solve today. That is the so-called code rank. The code rank is a known enemy for any automotive designers that appears when starting the engine. At this moment, the car battery falls to a low value for a short period of time and then rises slightly. As it can be seen in these two images, where the battery voltage is plotted, during cold rank, this battery voltage falls to a maximum of 3.2 volts and then rises slightly again. This profile depends on the motor conditions, and the most critical one is the ones with the motor where the motor is cold. As it has been said in the previous slide, some ADAS must ensure their functionality along all the time that car is in use. This is, the system must be immune to this car battery profile and supply a constant voltage level to the different sensors and cameras placed inside a common ADAS. In order to solve this issue, MPS had released a reference design aimed to keep the output voltage of the power stage at a constant level, regardless the input voltage. All the documentation about this design can be found in this link that is presented here. And as a general overview, this reference design consists on adding a bus converter between the input of the system, that is usually the car battery, and a common step-down converter that is seen in lots of automotive designs. The bus converter will convert the battery during cold run in order to acquire a stable voltage. Apart from this pre-bus will act also as an EMI filter, so we get low EMI noise. But there's a limitation, that is that at high output voltages, there's a low amount of available output power. So this design is not suitable for ADAS. In order to overcome this limitation, we have used the back-bus topology. This kind of converters contains 4 switches that, depending on their state, 3 different modes of operation can be obtained. As it can be seen, if the Q1 and Q2 is switching and Q3 is open and Q4 is closed, we get a back converter, and the back bus will act in back mode. So the output voltage will be lower than the input voltage. This is the preferred mode because it's where the high efficiency is obtained. The second mode of operation is the boost mode, where Q1 is closed, Q2 is open, and Q3 and Q4 are switching. In this mode, the output voltage will be step up from the input voltage. So the output voltage will be higher than the input voltage. The third mode of operation is the back boost mode, where the 4 switches are switching. And at this mode of operation, the input voltage and the output voltage are more or less at the same level. To see clearly what happens during cold crank, in this slide is presented how the converters will work theoretically. Assuming an output voltage of 5 volts, at the beginning of the profile, when the input voltage is around 11 volts, or the voltage of the battery, and it starts to decrease, the converter will work in back mode. Then there will be a short period of time where the 2 remaining switches will start to commute. That is where the voltage is around 5 volts. Third, when the input voltage will be in its minimum, that it's more or less 3.2 volts, the converter will work in boost mode and step up this voltage to 5 volts. Then the 4 switches will switch and we will get a back boost mode operation. And finally, we will get back mode. At this stage, apart from this kind of topology to be used in ADAS designs, it's also important to select the better IC to cover all the requirements. It has been said that the power demand with high output voltages is a must. Then the proposal that is done in this webinar is to use the MPQ8875A. This 4-switch synchronous back boost converter, thought to be used in Serson Fusher systems or camera monitor systems, is able to work in a wide input voltage range from 2.2 volts to 36 volts, supplying up to 5 volts of continuous output current. Other 2 important characteristics of this IC is the protection features demanded for some safety applications and the I2C interface. By this last feature, with the help of I2C interface, we are able to increase the flexibility of the design and reduce the number of external components. As for example, there are some chips that the soft star is configured by an external capacitor, as in this case, this soft star is configured by the I2C interface. We avoid to use an extra capacitor and to make any rework during the design. At this stage of the webinar, we have presented the problem that is to overcome the cold crank issue for ADAS applications, where the output power demand is high, while the output voltage required is also high. We have also presented the best option to overcome the problem, that is using a 4-switch synchronous back boost converter, and we also have presented the best candidate to be used, the MPQ8875A. Now it's time to present main tips to design this IC in order to get a stable voltage during cold crank. The first design tip is the inductor selection. We need to take into account that when the input voltage decreases up to 3.2 volts, as the output power must remain the same, the current through the inductor will increase. Then the selected inductor must have a saturation current higher than the maximum current that will pass through it. That is the sum of the current under cold crank conditions and the inductor ripple current. In this oscilloscope capture, we can see that by applying a cold crank profile at the input, seen in yellow, we obtain constant output voltage fixed at 10.5 volts in green. In orange is plotted the current that passed through the inductor. And as it can be seen, and as it had been explained, we have obtained a peak of 9.18 amperes during this when the input voltage reaches its minimum. For this reason, the selected inductor must have a saturation current higher than this maximum value. That will depend on the minimum input voltage and the selected output voltage, the efficiency of the AC, and the on the load current. Secondly, the IC must be configured taking into account this current peak. And for this reason, we must disable the overcurrent protection. This protection feature has a maximum limit of 9 amperes. And as it has been seen before, the obtained current peak is above this limit. For this reason, if it's not disabled, the IC will shut down and the output voltage will not be constant. On the other side, At normal input mode, the allowed input voltages range goes from 4.5 volts to 36 volts. In order to cover the full range of the cold crank profile, it's needed to set the low input mode, which allows a voltage until 2.2 volts. All these configurations can easily be set with the guide user interface of the chip. As it can be seen in this slide, the guide user interface has 2 pages with a huge number of available configurations, such as the output voltage, the compensation, some protection features, the frequency, the spectrum, switching frequency, and more. In this case, for applying the 2 settings that has been set before in the previous slide, we must change the input voltage placed in the first configuration page. And also, we need to change the overcurrent protection mode that is found in the second page of the guide user interface. Last but not least, it's important also to take into account the efficiency of the system, depending on the input voltage. As it can be seen in this plot, the efficiency changes notably depending on the converter operation mode. During back boost mode, the efficiency decreases. Then, depending on the application, it's needed to change the back boost thresholds to work as much as possible into the back mode, where the efficiency is over 98%. This means to reduce the range where the IC works in back boost mode. In this case, these efficiencies are obtained by setting an output voltage of 10.5 volts and sweeping the input voltage from 0 volts to 16 volts, and with 2 output currents set to 2 amperes and 1 ampere. By applying these few design tips, we are able to measure and get important conclusions about the performance of the MPQ8875A. Firstly, it's shown that the maximum output current depending the output voltage when the cold crank profile is applied. As it can be observed, the maximum current decreases when the output voltage is increased. For example, with a 3.3 volts of output current, we get a maximum output current of 4.3 amperes. But if we increase the output voltage until 10 volts, for example, where it's the common input voltage from some cameras, we get a maximum output current of 2.1 amperes. These analyses have been done by plotting the output voltage and getting the load current where the output voltage does not show any changes. If the output current overpasses this limit, the IC does not shut down directly. As it can be seen in this slide, when the current is higher than the allowed, in this case 2.5 amperes, the output voltage, that is plotted in green, decreases until the point where the IC can supply the maximum power. In this case, with an output voltage of 10 volts, when the input voltage reaches the 3.2 volts, the output voltage decreases 1.25 volts. Other important measure is the one that shows the maximum output current with a fixed output voltage of 10 volts. In this case, this test has been done by setting an output voltage of 10 volts, applying a cold crank profile, and changing this minimum input voltage from 2.5 volts to 7 volts. In this case, we can observe that with low input minimum voltages, we get lower maximum output currents. But if we increase this minimum input voltage, for example, in this case, is where the warm crank happen, we get high maximum output currents of above 5 amperes. As a conclusion, with the MPQ8875A, we can get high level of available power at low input voltage levels, making this solution a good candidate to be used in ADAS designs. Moreover, as it's only used a single IC, that most of the configurations can be set with the IC with the I2C interface, the number of required components is reduced, and consequently, the area is also reduced. An example of this reference design, an example of the application of the MPQ8875A is this reference design, which this back boost converter is placed into this design to supply the power to 4 different cameras and some other loads. An example of this operation is seen here, where we have applied an input voltage with a cold crank profile, And we also have get the output voltage that it's at 10.5 volts. This parameter is fixed by the I2C interface. We have set a load current of 1 ampere, and we can see here the peak current of the inductor and how it increases due to the Coltrane profile. And we also can see the switch nodes. In this case, the switch node 1, which is the back mode, the back switch node, is switching, and when once enters to Coltrane, it stops switching. So the IC will start working in boost mode, and then will return to back boost mode, because as the input voltage was 11 volts and the output voltage was 10.5 volts, the IC will work in back boost mode. That's all. If there's any question.
Okay, since there's no question, I might chime in. What came a little bit short, when the 8875A has an I2C interface, and it is also an, we call it OTP, it's a one-time program in memory. So all the settings of compensation, ramp, output voltage, so can be programmed into the device. Also, the current limits can be programmed into the device, and for a short period of time, even so we call it in a 5 amp system, or 5 amp part, the P current, which the part can switch for short periods of time, can be set up to 9 amp. So there's a lot of, say, short-term power capability. Typical time constant of the die is in the range of 1 second. So for short periods of time, you easily can overload the system. Any more questions? No? So just raise your hand or write it down.
So if there is no more questions, we are going to finish this webinar. Thank you for your attention, and we're looking forward to see you in the next webinars during this week. Thank you.